time domain as well as in continuous time as well as in discrete time. Now, second part is correlation. Already we know about this correlation concept in PTSP also. The entire last 2 units are entirely based on this correlation, autocorrelation or cross correlation. Again, here we are in this unit, we are going to discuss about this correlation. It is for signals. There the correlation concept is for random process. Here the correlation is for signals. Okay. Now we see the idea of correlation. First, we see the idea of correlation. The formula also, whatever the correlation formula in PTSP, whatever the correlation formula, the same formula we are going to use in the signals also. Now you see, whenever if we consider two different signals, that is x1 of t, x2 of t, one signal is x1 of t, another signal is x2 of t, then it is represented with correlation term R. So whenever there is a two signals, two random process in the PTSP, that is represented with xy. Now here instead of representing xy, we are going to represent with 1, 2. One represent for one signal, 2 represents for another signal. So in the formula also, you observe here integral minus infinity to infinity x1 of t, x2 of t minus tau dt complex conjugate. So there R12 of tau or Rxy of tau, there the formula is expected value of x of t into y of t plus tau, like that. The difference between the time intervals t plus tau minus t nothing but tau. Here also the same scenario. You consider the difference between the two intervals t minus tau minus of t, we are going to get minus tau. In our correlation, this formula is not only for t minus tau, we can also write for t plus tau. That can be the main idea of this correlation is one signal is fixed. X1, suppose x1 of t is fixed, any one signal is fixed. Another signal we are going to be delayed or we are going to be advanced. We are going to perform shifting operation on the another signal. That is the main idea here. So you observe in the formula x1 of t, in this formula x1 of t we are not disturbing. x2 of t we are going to be delayed here. That is whether it is delayed or it is advanced depends upon the tau value. Suppose tau is a positive, it is going to be delayed. Tau is a negative, it is going to be advanced. So the main idea is we are going to be test at different values of tau. Is there any similar information? The convolution is common area between the two signals. Correlation is we are going to find similar information between the two signals. Here in the formula, there is a complex conjugate. That complex conjugate indicates we are considering here the signals are complex signals. Suppose there is no any complex signal, even the complex conjugate of that signal is, suppose the signal is a real signal, the complex conjugate of real anyway, it is a real term. So that's why this formula we are framing for both real valued signals as well as complex valued signals. So that is the importance of this formula. This formula is already familiar in the PTSP topics. There we have represented the x of t, y of t. That is because of that concept is for random process. That's why there is a capital X of t, capital Y of t plus tau, like that we have represented. But here it is not a random process. It is a signal. Here we are in the signal systems. The concept of correlation is applicable for, we are applying for signals. So the idea of correlation is same. One signal is fixed. Another signal is going to be whether it is delayed or it is advanced. In the formula, wherever we have a complex conjugate, that indicates that we are applying for complex signals. So it is also applicable for real valued signals also. So that is the idea of correlation. You see this correlation is going to be represented R. It is very familiar because in the PTSP, we know about this R term. So R indicates correlation term. Tau indicates based on the tau value. Suppose it is positive, it is delayed. Whether it is a negative, it is advanced. We are going to be perform shifting operation on one signal. That is the idea of this formula. Now you observe this graph. In this graph, you see on y-axis there is a R12 of tau. On x-axis there is a tau. Now at tau is equal to 3, you see there is a highest value. At tau is equal to 3, there is highest value. So what does it mean? Between the two signals, whenever we are going to be compare the two signals, at tau is equal to 1, we are seeing. At tau is equal to 2, at tau equal to 3, at tau equal to 4, 5, 6 like that. Except 3, remaining all values almost it is nearer to 0. So whenever it is nearer to 0, whenever it is nearer to 0, yeah, madam. Yeah. Yeah, madam. Yeah. Okay. And whenever it is tau is 3, you observe here, there is a highest peak. So highest peak means there is a similarity is maximum. Remaining all values of tau, there is no any similar information. So we can conclude that these two signals are uncorrelated at remaining all values of tau except at tau is equal to 3. That is the main idea of this correlation concept. Okay. Now this formula we are going to be write in different ways. It is for real valued signals. Suppose the two signals are real valued signals, there is no any complex conjugate. The two signals are real valued signals, there is no any complex conjugate. And you see the same formula we are going to be write in different fashion. Here if you observe here, there it is a delayed version, here it is an advanced version. Now previous problem, the previous equation and this equation, we have obtained this shifting operation on second signal. We are obtaining this shifting operation on second signal. Now in this, the formula, it is not only limited for applying shifted operation for second signal. So that shifting operation, whether it is a first signal or it is second signal, both are same. The formula is right, no issue. Are you getting? One signal is going to be fixed, another signal is going to be shifted. In this equation and previous equation, we are performing shifting operation on second signal. Now you see this equation, second signal is fixed, first signal is going to be delayed or advanced. So that is the basic idea. You see here, it is going to be advanced, it is going to be delayed. Depends upon the tau values. So it is the cross correlation. Usually whenever two signals are there, the formula is nothing but cross correlation. Suppose we are performing this correlation operation on same signal, it is a autocorrelation. Now it is for continuous time. Whatever it is, the formula is for continuous time. Now if you write the formula for discrete time, instead of, again you see R12 of M, M indicates here instead of tau, in discrete time we are representing another integer M. Now instead of integration, it is a summation. Here you observe this signal is fixed. Another signal, whatever we are considering, it is going to be shifted, whether it may be a plus or it may be minus. If you write this complex conjugate, the signals, whatever the signals we are considering, these are complex signals. So the same formula we can also write. This time it is fixed, it is going to be shifted. So it is fixed, it is going to be shifting. We are performing shifting operation. So like that we can, overall we can write four equations. Means what first one is a, we can take x1 of t is fixed, x2 of t is going to be shifted, whether it is delayed or advanced, we will get two equations. Second case, we are going to be fixed the x2 of t, x1 of t is going to be shifted, whether it is delayed or advanced, again we are going to get two equations. Totally, we are going to get four equations, okay? Now, the relationship between convolution and correlation is, the correlation, instead of doing all this, whatever the calculation, anyway, we know already convolution. So that convolution concept, by using that convolution concept, we can obtain this correlation concept. So you see that one, the relation between convolution and correlation is, this derivation is not necessary, we will see later. Simply, you see R12 of M is equal to convolution between two signals. One of the signal is a time reversal. One of the signal is time reversal. That is the only thing. Again, there is a, between the two signals, it is one signal, it is another signal. Between them, there is a convolution operation. And you compare this one. Previously, what is the convolution formula? Suppose there is a general convolution means x1 of n convolution with x2 of n. But here, one signal is time reversal, another signal is as usual. Then if you perform convolution, you are going to be get correlation. So it is the relation between correlation and convolution. It is for discrete time, it is for continuous time. You see here, R12 of tau is equal to x2 of tau, x1 of minus tau, convolution between these two. You suppose you know the, if you apply Fourier transform of x1 of tau, it is nothing but x of omega. Suppose if we apply Fourier transform of x complex conjugate of t, this formula is x complex conjugate of minus omega. Suppose if we apply Fourier transform of x of minus t, you know it is a complex conjugate of x of omega. These formulas already symmetry properties we have seen in Fourier transform. Suppose if you want to write it is in Fourier transform formula, if we apply Fourier transform for this, Fourier transform of this R for discrete time signals, we need to go for application of DTFT. We can apply the DTFT formula. Here it is a continuous time Fourier transform. For showing the difference between it is a DTFT, it is a continuous time Fourier transform, we are showing this omega. This omega is for DTFT, this omega is for CTFT. We can follow this omega, both omegas with this omega only, no issue. But we are showing for differentiating the discrete time and continuous time. You see here, it is a, what is this mean? Fourier transform pair. Fourier transform, this cross correlation is equal to, there is a two signals convolution. Convolution in time is multiplication frequency. So as usual, original signal DTFT is x2 of omega. Here there is a time reversal. So here is a time reversal. Whenever there is a time reversal, you observe this one. Whenever there is a time reversal, it is a complex conjugate. So one is a x2 of omega, another one is complex conjugate of that particular DTFT or continuous time Fourier transform. It is the relation between continuous time to frequency domain. Okay. Now, the concept of correlation, if you apply for power signals, the concept of correlation, if you apply for power signals, we know what is mean by power signal. We know one statement. Most of the periodic signals are power signals. So the signal is a periodic signal. The signal is a periodic signal. So it is going to be repeated with some fundamental period. The signal is a periodic signal. The signal must be repeated with some fundamental period. So the power signal means we are applying this concept for periodic signals. The formulas all are same. Only thing is, instead of applying from minus infinity to plus infinity, instead of applying from minus infinity plus infinity, we are going to be write from minus t to plus t. So whenever there is a minus t to plus t, always we need to write the difference between these two, upper limit to lower limit. Upper limit is t, t minus of minus t is 2t. So along with this, usually the limit is, actual limit is from minus infinity to plus infinity. That's why we are writing limit t tends to infinity. Limit t tends to infinity, 1 by dt integral of minus t to plus t x1 of t. This formula is same. Only thing, for the concept of power signals means we are going to be apply for periodic signals. We are going to be apply for periodic signals. It is for continuous time formula. Now coming for, it is for discrete time formula. So it is also a continuous time formula, but it is for complex signals. It is for real valued signals. Whenever there is a complex conjugate, the two signals we are assuming these, there may be a chance of considering complex signals. Suppose the given signal is not complex signal, this formula is sufficient. Okay, we can also write the formula. Previously we have written it is a delayed operation. It is going to be right advanced operation. Same for every equation, every relation. We are going to be frame four possible equations, because one is fixed, another one is going to be delayed or advanced. Suppose x1 of t is fixed, x2 of t we are going to be delayed or we are going to be advanced. Similarly, x2 of t is fixed, x1 of t is delayed or advanced. Okay, it is the delayed concept, correlation concept. Now, similarly, you can write for discrete time also. Whenever a discrete time periodic signals, we know periodic signal means it must be some fundamental period. So the fundamental period we are considering here some n. Instead of considering integration, whenever we are going for a discrete time, we can consider a instead of integration, we can consider it is a summation. So whenever it is a summation and the interval, the total interval is here, he has not written n plus 1. You need to write here n plus 1. Suppose always we need to write minus n to plus n, or otherwise finally we can consider some n samples 10. It is also get 10. Suppose whenever it is a negative to positive, you write here 1 by n plus 1, limit n tends to infinity. This formula is same. This formula is same. It is about discrete time correlation periodic signals. Discrete time correlation for periodic signals. Now, coming for autocorrelation. So, in the autocorrelation, the name itself, autocorrelation, in the previous case, we have considered two signals. Here, we are not going to be consider two signals. We are considering the same signal, just the signal is going to be delayed, and then we are going to be again see at what value of t. Suppose we are transmitting a signal, one signal, suppose we take a radar concept, we are transmitting the signal from radar, it is going to be identify the object, and again it is going to be reflected back. So the same signal is reflected back. Now, how much delay is taken to identify that target or object? How much time it is going to be taken? From this, we are going to be, from the correlation concept, we are going to be identified. So at what time we are going to be get a relation between the two signals, at what time is maximum. So autocorrelation means same signal, same formula, only thing x1 of t is equal to x2 of t. So that is the concept of autocorrelation. That's why whenever there is autocorrelation, no need to write 1, 2, simply R. Again, what is R? Correlation. Autocorrelation means R of tau. Integral minus infinity to infinity, x of t, again x complex. Previously it is x1 of t, x2 of t. Here no need to write x1 of t, x2 of t. You can simply write x of t. Okay, that is the difference between autocorrelation and cross correlation. Okay, again if you want to write formulas, here we can write another formula plus tau. Another case, here in the autocorrelation, we are going to get only two signals, because signal is same, whether it may be delayed or it is advanced. So another formula, we can write it is a advanced formula. Similarly, it is for continuous time. Coming for discrete time. So discrete time means like tau, a dummy variable, we are going to be consider another variable is m. And instead of integration, we are going to be consider summation. Original signal is x of n. Another signal is we are going to be delayed or advanced, depends upon this m value. Okay. Same formula. We are changing the integration to summation, variable tau to m. So usually in the PTSP, the difference between these two, t plus tau minus t, we are going to get tau. That is the same fashion here. Okay. Now, you see overall conclusion, the formulas of autocorrelation. Suppose if you apply for periodic signals, autocorrelation for periodic signals. So periodic signal means it must be some fundamental period. So the fundamental period is minus t naught by 2 plus t naught by 2. That interval is t naught. So 1 by t naught minus T naught by 2 plus T naught by 2. That signal is same. One signal is x of t fixed, another signal is delayed or advanced. So the concept we have applied for complex signals, you can write it as a complex conjugate. Suppose it is a real valued signal, it is a real value. No issue with that. Okay. So it is the formula of autocorrelation for periodic signal is power signals. Now it is for continuous time. Again, if you want to write for discrete time, instead of writing summation, we can write here integration, we can write here summation with some fundamental period for autocorrelation. If you know cross correlation formula, it is autocorrelation is simple because the same signal. Now write down next one is relation to signal energy and signal power. How can you calculate the energy of the signal? How can you calculate power of the signal? Now you see, you consider the autocorrelation formula. What is the autocorrelation formula? R of tau, integral minus infinity plus infinity. One signal, you can consider x of t. Another signal is going to be delayed or advanced, and then it is complex conjugate. Here it is delayed by tau. Why it is a tau? Suppose it is some other variable p, it is a p. Some other variable k, it is k. Okay. That depends upon, we are going to the shifting operation is depends upon this value. Or otherwise we can remember just the difference between these two, we are going to be represent here. The difference between these two. Okay. So t minus of minus t minus tau. So you will get here tau. Okay. No issue with that. One is original signal, another one is complex conjugate. Okay. In this formula, if we substitute tau is equal to 0. In this formula, if we substitute tau is equal to 0. So whenever tau is equal to 0, x of t, complex conjugate of x of t. X of t, complex conjugate of x of t. We know the formula x of t, whenever complex conjugate of x of t, it is going to be right magnitude of x of t whole square. X of t, complex conjugate of x of t is magnitude of x of t whole square. So we know what is the energy of the signal. How can you find out the energy of the signal? Energy of the signal is, we know the formula integral minus infinity magnitude of x of t whole square dt. So it is simply the energy also we can calculate from autocorrelation. So we can write autocorrelation formula simply R of tau integral minus infinity to infinity. One signal is fixed. The signal is x of t fixed. Another one is we are going to be operate whether it is delayed or it is advanced. So that is our choice. And then we can apply complex conjugate. We are writing the formula for complex conjugate. Initially for complex conjugate, the signal is not a complex signal. No issue with that. It is a real valued signal. No issue. So like that we can calculate energy. The same concept already we covered in PTSP also. PTSP also we have calculated the power or energy. Now, how to calculate power? The only difference is for energy, we are going to be consider total interval from minus infinity to plus infinity. Power means we are going to be consider periodic signal. That is the only difference. The formula and everything is same. So that's why you can write limit t tends to infinity 1 by t. The interval is from minus t by t to plus t by 2. X of t as usual same. Another one it is going to be delayed and it is going to be complex conjugate. And then whenever if you substitute tau is equal to 0, you see the formula limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2 x of t x complex conjugate of t dt. So x of t x complex conjugate of t we know magnitude of x of t whole square. So what is this one? Power. The only difference is whenever it is power we are calculating the power, we are going to be consider periodic signal. Whenever we are going to be calculating energy, we are going to be consider aperiodicity, means the interval is from minus infinity to plus infinity. Whenever it is a periodic signal, that is going to be periodic with some fundamental period. So the limits we are going to see whether it is a 0 to t or minus t by 2 to plus t by 2 or minus t to plus 2. Like that we are going to be consider that limits. That is the difference between energy and power. Now one more very important in this topic is properties of autocorrelation. Properties of autocorrelation. So these properties also, autocorrelation properties also already you covered in PTSP, but in that there is a random process capital X of t is there. Now in this, instead of capital X of t, here we are going to write small x of t, because here the concept we are applying for signals. The concept we are applying for signals, not for random process. That is the difference between PTSP autocorrelation concept and your signal systems autocorrelation or cross correlation concepts. Now, the first property is R of tau is equal to R of minus tau with complex conjugate. R of tau is equal to R of minus tau with complex conjugate. So, what does it mean? What is R of minus tau? Time reversal. With time reversal means we are going to be fold the signal with respect to vertical axis about the origin. R of minus tau means fold the signal with respect to vertical axis about the origin. Okay. So, now you write R of tau formula. What is R of tau? Integral minus infinity to infinity x of t into x complex conjugate, and it is going to be shifted whether it is delayed or advanced, t minus tau dt. It is the R of tau formula, correlation formula. Now, if we apply complex conjugate for this, so entire thing is complex conjugate. So it is going to be complex conjugate. Already it is a complex conjugate, so it is going to be get like this. Now, if you write this, t is replaced with minus tau. T is replaced with minus tau. Then integral minus infinity to infinity x complex conjugate of t, x of, it is going to be minus tau means tau is plus, here minus, it is going to be plus. Now it is the formula for again autocorrelation, R of tau. So that's why R of tau is equal to R of minus tau with complex conjugate. Now, second property. Previously, whatever we have derived how to calculate energy, it is we are going to write for one property. Now, you consider the R of tau formula as usual. In this tau, you can substitute tau is equal to 0. Now, you see the formula x of t into x complex conjugate of t minus tau into dt. Whenever if we substitute tau is equal to 0, you will get x of t into x complex conjugate of t. So, it is the magnitude of x of t whole square. So what is the magnitude of x of t whole square? It is nothing but energy. So R of 0, whenever if you want to calculate energy from autocorrelation, then you can write the autocorrelation formula and you substitute tau is equal to 0, you will get the energy of the signal. Now see the third one. R of 0 value is maximum compared with the remaining tau values. Okay? The tau is equal to 0, whatever we are going to be get in the autocorrelation function, that is the maximum remaining all values of, compare with the remaining all values of tau. So, that relation we are going to be prove from this. Now, you see here, x of t plus or minus x of t plus tau. What is this one? It is a one signal, x of t. The same signal is going to be delayed. X of t, whether plus operation or it is minus operation, and if we take a whole square, is always greater than 0. Anyway, we know x of t, one value, plus x of t plus tau, that is the same signal, it is going to be delayed, and it is whole square is always greater than 0. So that is we are representing here. Whole square means x square of t plus another signal x square of t plus tau, and plus or minus 2ab, that formula greater than or equal to 0. And then we can write it is same operation greater than or equal to plus or minus this one. And then if we apply integrating on both sides with interval from minus infinity to plus infinity with respect to t. And then what is this one? Energy of the signal. What is this one? Another energy of the signal greater than or equal to 2 into, you observe this one. It is nothing but autocorrelation. So R of tau. So what is this E? Energy of the signal, E plus E, 2E, 2 gets cancelled. E is greater than or equal to R of tau. You know what is the E? R of 0. So R of 0 is greater than or equal to R of tau. So one more important property, already in the PTSP also, we discussed about this one. In between autocorrelation function and power spectral density, there is a pair forms Fourier transform pair. So Fourier transform of R of tau, we are going to be write Fourier transform of R of tau, we are going to be write some S of omega. S of omega. So it is going to be right, S of omega is equal to integral minus infinity plus infinity R of tau into e power minus j omega tau into e power minus j omega t into dt. Like that we can write. So that is going to be represented here, some psi of f, psi of f. So Fourier transform of R of tau is psi of f. Inverse Fourier transform of psi of f is R of tau. So that means Fourier transform of autocorrelation function, we are going to get spectral density, energy spectral density. Or there, most of the time we are calling it as a power spectral density. No issue with that. Okay. Similarly, these are all are same for periodic signals. Periodic signal means only difference is ఈ క్లాసు ఇంకొక 5 minutes లో క్లోజ్ అవుతుంది. తర్వాత అగైన్ మళ్ళీ స్టార్ట్ చేస్తుంది, మళ్ళీ జాయిన్ అవ్వండి. ఎందుకంటే ఇది 40 minutes ఉంటుంది కాబట్టి జూమ్లో. అగైన్ యూ కెన్ జాయిన్. The same, whatever the formula, the same formulas are also applicable for periodic signals. Only thing is, instead of writing minus infinity to plus infinity, we are going to be write here minus t by 2 to plus t by 2, and whatever the difference between these two, that is going to be write 1 by t, and we are keeping here limit t tends to infinity, because that actual limit is from minus infinity to plus infinity. That is going to be, we are limiting for periodic signal. So remaining all properties, whatever it is, all are applicable here. Only thing, the first property is same. Second property, instead of writing E, we are going to be write P, because it is a power, because it is a periodic signal. Suppose the interval is from minus infinity to plus infinity, it is the energy. The interval is from minus t naught by 2 to plus t naught by 2, it is the power. That is only a difference. Okay. Now you see one problem on this, how to prove this one. Find the average autocorrelation function of the sine wave signal. Find the average autocorrelation function for the sine wave signal. Okay. Now you see here, find the average autocorrelation function. Find the average autocorrelation function of sine wave signal. Now the signal as given, x1 of t is equal to a sine omega 1t plus tau, a sine omega 1t plus tau, where usually in the PTSP every time we are going to call wide sine stationary, wide sine stationary, wide sine stationary. What is the meaning of wide sine stationary? It is the whatever the autocorrelation function, it is not function of time. It is not function of time. It is a independent of time. That is the concept of wide sine stationary. Here it is not a random process. Here we are considering the signals. Here we are considering the signals. That's why that point, that word is not necessary here, whether it is a wide sine stationary or not. Now here the idea is x1 of t is a into sine omega naught t, a into sine omega naught t, sine omega 1t plus tau, where you know omega 1 means fundamental frequency, that is going to be right 2 pi by t1 or 2 pi by t0. Now you need to calculate autocorrelation function. So R of tau is equal to, because it is given with some fundamental frequency, so we need to write the formula for periodic signal. 1 by t naught integral minus t naught by 2 to plus t naught by 2. One signal x1 of t or x of t is same. Another time, one time it is fixed, another time we are going to be delayed or advanced. Suppose it is maybe delayed or it may be advanced, we can write t minus tau or t plus tau complex conjugate. No issue with that. Okay. Anyway, the signal is a real signal. So even if you apply complex conjugate for this, we will get the same signal. Okay. Now coming for this formula, limit t tends to infinity, 1 by t integral minus t by 2 to plus t by 2. The formula, the same formula, we can also write like this: x complex conjugate of t, x of t plus tau dt. No issue. Whether you use this formula or use this formula, both are same. Both are same. So the complex conjugate of the given signal is same because it only there is no any complex term. So you can substitute limit t tends to infinity 1 by t integral minus t by 2 to plus t by 2, whatever the x of t you can write here. What is the t? Where is the t? T is going to be replaced with t plus tau. You can write this formula. And then we have a formula sin A sin B. You see here the formula 2 into sin A sin B. You just multiply and numerator and denominator. Multiply with numerator and denominator with 2. So we can write 2 into sin x sin y is equal to cos A minus B minus cos A plus B. So that's why in the denominator we are going to get 2. And there is a into a square you can write outside, and integral minus t by 2 to plus t by 2 sin A minus B sin A 2 sin A sin B is cos A minus B plus cos A